I have a very bad news for you, and that is you are not perfect. Well, um, if that's not bad enough, then let me tell you something worse. You cannot be perfect. Well, there's nothing personal. It's just that perfection is impossible, theoretically impossible, let alone practicality of it. It's theoretically impossible to achieve. Well, I'm not talking about the spiritual aspect or anything related to spirituality, but if I consider just the physical life form that is you, I mean your physical life form, then in this physical world we cannot have anything that is absolutely perfect. It's impossible. Well, let me break it down to the simple concepts of physics. Okay, so let's say that we are all thermodynamic systems, right? We are all thermodynamic systems, aren't we? um, that is, well, we do some work, but then how do we do work? We basically get some heat from a higher temperature heat source, and then we reject some heat. Let's suppose this is our physical body which works as an engine, and then we reject some heat. We take some heat, QH, uh, from the high temperature body, and then we reject some heat to a low temperature body, and that heat rejected is QL, where TH is greater than TL, right? That is high temperature, low temperature, well defined now. And in this process, while the heat flows through us, we do some work, and this work helps us achieve our objectives, right? So basically, we are heat engines, aren't we? Or, well, there is one difference between an ideal heat engine. It can be reversible, at least theoretically, and it can be used as a heat pump. That means it can take heat from a low temperature body and supply heat to a high temperature body, provided we give it enough amount of work, right? But then this process, this is basically, let's get into the simplified, the most simple form of any heat engine, right? Basically, I have already simplified all of us to simple thermodynamic systems. Then I simplified all the thermodynamic systems into basically a simple heat engine, and then I'm further simplifying things into a what do you call, a Carnot's engine, right? A Carnot's engine is operates like this, right? He takes heat from a high temperature body, always at a constant temperature, takes QH amount of heat, right, and rejects QL amount of heat to a low temperature body. Again, the temperature is constant there as well, and in the process, it delivers some work like we do. Yes. Now, if it's a Carnot's engine, which is a theoretical reversible engine, that means no dissipation happens here. No dissipation. You might say, okay, well, imperfection is introduced because of some dissipations to the surroundings, right? Heat, loss of energy. Well, if assume there is no dissipating or dissipative agent present, no friction, no air resistance, nothing that could take away any energy or leak any energy from you, still perfection is impossible. And in this lecture, I will help you understand why that is. Now, Carnot's engine has an efficiency given by 1 minus QL by QH. And this particular efficiency is less than, always, or equal to the ideal efficiency, right? It's the normal efficiency for any engine. Uh, well, there could be dissipations there, but if you remove all the dissipations, the ideal engine, well, no dissipation happens, then the ideal efficiency will come out to be 1 minus TL by TH, right? That's the ideal efficiency. See, which is the maximum possible efficiency. Okay. That means if we talk about perfection as ideal efficiency, if perfection is defined as 100% efficiency, then it's simply impossible to achieve. And I will explain that again. So, if you haven't understood already how the efficiency of a Carnot's engine is derived and how the maximum limit, that is the eta ideal or ideal efficiency, is derived, you can watch the lecture that I had delivered previously. I will put a link in the description as well as, if possible, somewhere as a card. But now, go watch this right now and then come back here, right? So you will understand this lecture, make the most out of this lecture. Clear? Now understand this. Uh, why can't we have maximum efficiency? Let's understand. If general efficiency is expressed as 1 minus the heat projected to the surrounding minus the divided by the heat taken from the surrounding, right? Then because of this factor, eta is getting less than 1. Yes or no? Why can we have the heat loss to be 0? That means we, from a high temperature body, we simply take QH amount of heat, right? And we convert all of them into work without ever needing any low temperature body, right? We can deliver all of it as work. It's still impossible. That is because of the Carnot's theorem, right? Which I have already expressed and proved the Carnot's theorem in the same video that I was talking about. Check the description for the link of that particular lecture, or the card might flash somewhere right now. But understand that this is still impossible, and this thing has to do with the ideal efficiency definition. Okay, let's go to that. The ideal efficiency definition is going to be super fun. Stay along. Okay, 1 minus TL by TH, right? What if we make this factor as 0? If we can convert that to 0. So basically, if I take TL by TH to be equals to 0, that means my low temperature body should be exactly at 0. What 0? 0 Kelvin, absolute scale temperature. It should be 0 Kelvin temperature, and that is where the problem lies, that 0 Kelvin is impossible to achieve. It is the impossibility approach. Impossibility approach or impossibility interpretation of the third law of thermodynamics. Third law of thermodynamics. Okay, that is 0 Kelvin is theoretically impossible to achieve. And there are a lot of popular text on the internet and textbooks which actually varying from simple explanations to very complicated mathematical explanations. That's it. It's not okay. It's 0 Kelvin. That is theoretically impossible to achieve. But I'll first give you a very general description. What's the third law of thermodynamics? See, just like the conservation of energy principle, on which the entirety of physics is based, and to your surprise, I would say that the principle of conservation of total energy, which says that for an isolated system, the total energy is basically constant, right? For an isolated system, if I have an isolated system, that means no exchange of mass equals to 0. Exchange of energy is also 0. So mass and energy are not being exchanged between the system and the surroundings, right? Not exchanged. No mass, no energy. Exchange happens, right? It's an isolated system. So whatever is the total energy of the system, that energy remains constant. That also means that energy, this particular energy might change from one form to the other, but it is neither going to be created nor going to be destroyed completely. Okay. So, but then let me tell you this, that this principle of conservation of energy is not conclusively proved yet. And all of physics is based on an assumption, which actually I would say a conjecture. Uh, and so far it has been worked surprisingly well, although it has not totally been disproved or conclusively been disproved or proved. There is no available conclusive proof for this. Okay. However, it has managed to work, and it has taken us from the cave to today's skyscraper. So, and even much beyond to space. So I think that's good enough assumption or conjecture, I would say. Okay. Now, similarly, this particular the third law of thermodynamics, it actually still, actually, it has not gotten any conclusive proof. Trust me, scientists, physicists are still working to have a very conclusive proof of the third law of thermodynamics that yes, this is true, this works. So far, this has been working, but no conclusive proof has yet been established. Okay. Still research is going on, but let's say that, okay, let's understand why it is conceptually correct. The What does it say? The general statement of the third law of thermodynamics says that the entropy of a system approaches a constant value when its temperature approaches absolute zero. So what does this entropy means? It's basically the degree of disorderness or degree of chaos in a system. Okay, and to understand more, again, do watch the video that I am referring to. Find the link in the description. So the entropy of a system approaches a constant value when the temperature approaches absolute zero, right? That means, yes, if I start with an entropy x1 and reduce my temperature towards absolute zero, it's in Kelvin, right? Then it will reach a constant value. This constant value might be zero, and yes, it is zero for a properly perfectly crystalline solid. If it's a crystalline solid, it will be the entropy itself will be zero, but it might not always be what do you call a crystalline solid, right? There could be a lot of more than one microstates, right? In that case, there would be some entropy, and that will be the limiting entropy for that particular system. Now, if I start with another entropy state for the same system, x2, and gradually reduce my temperature, I'll reach that. Let's call it S0, the entropy at 0. So S0 is greater than or equal to 0, right? It for the perfectly crystalline solid, at absolute zero, the entropy will be zero. But if it's not a perfect crystalline solid, then there could be some non-zero entropy, which actually is the case. So what happens if I basically let's understand this. Okay, let's understand this interpretation that is given by Nernst interpretation. Nernst, a famous physicist, actually interpreted the third law of thermodynamics and said that it is impossible for any process, no matter how idealized, to reduce the entropy of a system to absolute zero in a finite number of operations. In a finite number of operations. So basically, we are taking a particular system at a certain temperature and then trying to cool it down to absolute zero while trying to reduce its entropy, right? So let's understand what that means. Again, if you have already covered the video that I was referring to, where I have explained entropy and Carnot's theorem. So let's understand this. From a higher state, x1, which is greater than x2, if I start with a higher entropic state, let's say, and then I'm basically going to a less entropic state, x2, right? Now, what happens is, at a particular temperature, I extract some heat, let's suppose Q1, and thus I am reducing the entropy at the same temperature. Then what I do, I go through, this is an isothermal process, right? Isothermal, because the temperature remains constant, just like, in a Carnot cycles, isothermal. Now, heat extraction has happened and entropy has reduced. Now what I do, I go to a lesser temperature and adiabatic expansion, and then there is no heat exchange happens here. But now here, after reaching a lower temperature, I again extract certain heat, Q2, again isothermal. Then I go to a lesser temperature, then I extract some more heat, Q3, then I go to a lesser temperature, and as the difference between these two states, x1 and x2, is keeping on decreasing, right? I'm approaching, absolute zero. Then see, there are no, after a certain while, especially while I'm close to here, like if I put it in red, while I'm here somewhere, right, at this temperature, can you actually tell me how many finite steps are there? No. It's impossible to count how many steps, because it will be infinitely large number of steps. So basically, if I tell you how many numbers are there between, how many real numbers are there between 0 and 1 on a real number line, right? If this is a real number line, then from 0 to 1, how many numbers, real numbers are there? Infinite, right? So similarly, there are infinite number of steps. So basically, by reducing the temperature of an object, of a system, from any given temperature to absolute zero requires infinitely large number of steps. Thus, it is impossible to achieve 0 Kelvin. There is another famous explanation also, very commonly used explanation, and that explanation would be, let's see, we have already covered. Okay, now we have, see, the reason why it is impossible to have a 100% efficient engine is because it's impossible to attain 0 Kelvin. And now we are trying to understand why it is impossible to attain 0 Kelvin. Okay. So now let's 0 Kelvin. To cool certain things, let's suppose, for example, if I have a body at 100 Kelvin and I want to reduce the temperature to, let's say, 100 Kelvin to 90 Kelvin, right? How would I do that? So basically, I'll have a body which is at a lesser temperature than the current temperature, right? But this lesser temperature body can go, theoretically, let's say, it can only go up to 0 Kelvin, right? So the higher temperature body will always be at certain temperature which will be greater than 0 Kelvin, because the low temperature body cannot fall beyond 0 Kelvin, right? To drag you, to pull you down, I have to be below you, right? But if I'm already standing on the ground, if I cannot dig deeper into the ground, so max to max I can bring you to my head, right? So that's how it happens, right? So to cool something down to a low temperature, you need to have a body which is less than the desired low temperature. But the desired low temperature cannot be lower than 0 Kelvin, hence you cannot cool it down. That's a very layperson's explanation actually, okay? So, but you can take it as an explanation. Now, I would rather go on to give you one of the on the basis of something even more amazing. I can, beyond these two explanations, I'm going to give you another reasoning, a quantum mechanical reasoning rather. Why is it impossible to attain 0 Kelvin? Let us go towards it, right? Have you heard of the uncertainty principle? The uncertainty principle. In quantum mechanics, what it says is that for any particle which might be moving at a velocity and might be at a certain point x, y, z. Let's suppose, let's ignore the y and z. Let's suppose there is a particular particle on the x-axis, right? And it's moving with a velocity v, right? With a mass m, right? Or you can just say that it's got some momentum. Let's suppose it's got some momentum p, right? So its position at any given point is x, right? At any given time, the position of the particle could be x. The uncertainty principle says that if the product of the uncertainty it's in its position and the uncertainty it's in its momentum along the x-axis, let's say, is greater than or equal to a constant, a positive constant known as h by 4 pi. What is h? H is Planck's constant. Planck's constant. and that has a value around 6.626 into 10 to the power minus 34 joule per second, right? And 4 pi is you know what the value of 4 pi would be, so it's a positive constant. So the product of the uncertainty between the product of the uncertainty in position as well as in the momentum in that particular positional axis will always be greater than or equal to h upon 4 pi, right? That means if you know 100% well, that means this delta x, let's suppose you know the momentum exactly, the value of the momentum to be precise. So if this uncertainty is 0, that means you are 100% certain the uncertainty here will be infinity. What does that really mean? Does it really mean being uncertain? Being uncertain means, well, there are two ways to understand this, right? Well, the word uncertain means, well, while measuring, you might not have good enough instruments. Your measuring instruments or measuring technique may be flawed. Well, that's not the case when we talk about the quantum mechanical uncertainty principle. That simply says, let's understand what that says. Now, if I have, for example, let me take the x-axis. Okay, let me just explain that on the basis of the x-axis. Yeah, and let me give it a red color. Right now, understand this. When we talk about a particle, it's actually not always a particle. Everything in nature, everything, I'm talking about everything in nature, especially you talk about a mass and a particle with mass or massless particle, whether it's a particle of matter or a particle of force carrier, like the photon, for example, you will always have two natures, the dual nature. What are those? It will have a wave nature and a particle nature, right? Not just light, everything, including you. So what really happens to you when I talk about your wave nature? It's basically you know, your characteristics can be described as a wave, but it would be very crude because you know your size has grown. You are basically a collection of a lot of particles. But imagine a small scale particle like a photon, an electron maybe, right? In that case, its wave nature would be non-ignorable as compared to its particle nature. So you wanna have to respect both aspects of that particle, right? So when I say that a particle is moving, let's talk about what is uncertainty in its momentum, right? When you talk about momentum p, you basically are talking about velocity, right? Take the mass factor out, you get the velocity. And what exactly is velocity? Well, the velocity, let's suppose along the x-axis, let's say this is my x-axis, right? So the velocity along the x-axis is the rate of change of the x coordinate with respect to time, right? Or if you don't understand calculus very well, then let's suppose the change in its position happening over a small period of time when the period of time is almost zero, like 0.00001 second. Okay, if you want 0.0000001 second, in that time interval, what is the change in its position happening? You see, this velocity of the particle by definition includes the uncertainty in position. Yes or no? Another way to visualize this is that when something is moving, you can consider that to be moving from, let's suppose, a point here, let's call this point A, to a point B, and there could be a wave that you can consider that is progressing with the velocity or the speed Vx from A to V, a wave. It might not always be a simple cosine or a sine wave, any wave, right? So the particle basically, it's most, it is called de Broglie wave also, or matter wave. A particle can be interpreted as a wave. A particle, basically a moving particle, can be interpreted as a wave between two certain points A and B, right? Two different points, not equal, right? Two different points separated in space. And the speed, if it's a simplified wave, very singular wave, then you can simply say the wave speed. But it could be basically a superposition of multiple waves. It could be a superposition of multiple waves if I write that like this. Right? If there are, two or more waves which are basically, they are being superimposed, that means the particle that we're talking about is not just a single particle. It's basically a collection of multiple particles, just like we are, right? A lot of we are a result of a lot of waves if we consider ourselves as matter waves. So in this case, the term wave speed could be taken as group velocity, or the wave velocity can be interpreted as group velocity or phase velocity. A little bit complications, which I don't want to get into right now in this. So basically, when we talk about a particle moving from one place to the other, the motion itself has an inherent wave nature. And when we talk about a wave, look at any of these waves between A and B, there is an uncertainty. Let's suppose this is 0 and this is at any B is at any distance x. So there is some uncertainty in its position. Where exactly is the wave right now? It is anywhere between A and B, right? So that introduces some uncertainty. So the moment when you talk about the velocity, it also introduces some delta x. However, if you just consider a particular point, let's suppose this is where the particle is right now. This is where the particle is right now, and it has basically a precise velocity, a position. Let's suppose x naught. That's its precise position. If I consider that precise position, then at that moment I would have no idea where is it moving, because to know how fast it is moving, its speed, I'll have to give it some time to change its position so that I can find its velocity, correct? So the moment when I focus too much on the particle nature, the wave nature makes no sense. And when I consider totally about its wave nature, the particle nature makes no sense. So when you combine both the concepts, the position and the momentum, or the position or the velocity, what really happens, the nonsensical paths add up. I mean, they get multiplied and leave you with the uncertainty principle, as we have discussed. So this is the inherent, the uncertainty principle is an inherent law of nature. Okay. So understand this, the uncertainty in its position and uncertainty in its momentum is greater than or equal to h by 4 pi. Minimum uncertainty will be h by 4 pi. It could be more than that, right? Clear? Uncertainty principle. Now let's come to 0 Kelvin. What is 0 Kelvin? 0 Kelvin is absolute zero on thermodynamic scales. That means there could not be any temperature which is less than 0 Kelvin. There cannot be any temperature which is less than 0 Kelvin. Why is that? Because the concept of temperature, especially the reason why the absolute temperature scale by Lord Kelvin was introduced, is that he wanted a physical interpretation to, very accurate physical interpretation of temperature to the motion of the particles of a system, right? So basically, the temperature of a system, temperature in absolute, okay, in absolute scale, is a measure of the K average, the average kinetic energy of a system. Let's suppose a system has a lot of particles. Okay, a system has n number of particles, right? So basically, the K average will be the kinetic energy of the first particle plus kinetic energy of the second particle plus so on and so forth up to the nth particle, and divide that by n. And what is kinetic energy? The kinetic energy is half of the mass in a non-relativistic scale here into speed squared, right? So it could be Vx squared, Vy squared, Vz squared, whatever you can say, right? And not always this expression. If it's rotating, then it will be a rotational kinetic energy also. If it's vibrating, it's vibrational kinetic energy also, right? So basically, the average kinetic energy of a system is equal to the number of degrees of freedom multiplied by the constant which we call Boltzmann constant multiplied by temperature, right? Understand this? The average kinetic energy of a system is basically the number of degrees of freedom multiplied by the Boltzmann's constant multiplied by the temperature in absolute scale. Okay, that means on Kelvin scale. Now the average kinetic energy, basically if I convert this formula, so if I take the absolute temperature as 0 Kelvin, definitely put that into the equation, you will say that the average kinetic energy will be 0. Fine. What is the problem in that? Well, when we talk about the average kinetic energy, we have the number of particles, 1 by number of particles multiplied by some constant, let's suppose K1, I will say C1 for half M, right? Or any equivalent in case you are taking the, what do you call it, the relativistic kinetic energy concept. Let's fix all of that into a coefficient. C1 is a constant into its speed squared, right? 1 for C2 V2 squared plus C3 V3 squared plus dot 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 up to Cn Vn squared, right? Can we consider that? Yes. So basically that is 1 upon n, then summation of Cn Vn squared, n equals to 1 to n. Let's suppose this is I, Ci Vi squared, I equals to 1 to n, right? That's the average kinetic energy. See, it's a sum of squares, right? And squares cannot be negative, can they? Now, if there are certain squares which add up to 0, that what does that mean? That means each and every one of them has to be 0, right? Every one of them has to be 0. Otherwise, the sum cannot be 0 because squares cannot be negative. Yes or no? So, if I take the absolute 0 temperature as 0 Kelvin, then the average kinetic energy will be 0. That also means that I cannot take T as negative. If I take T absolute scale temperature as negative temperature, then average kinetic energy should be negative, which is impossible. That means I cannot have a negative Kelvin temperature. And that is exactly why it explains that since I cannot have at a negative, at a temperature at a negative Kelvin, so I cannot cool anything which is at a high temperature to 0 Kelvin. Because lowest possible mark is 0 Kelvin. But the 0 Kelvin is still impossible to achieve. How do we explain that? Well, at 0 Kelvin, the ith particle will have average kinetic energy is 0. So let's explain that. The average kinetic energy is 0. That means for any particle, right? So basically the energy of the ith particle is also 0. That means the velocity or the speed of the ith particle is also 0. That means the momentum of the ith particle is also 0. If I take 0 Kelvin temperature, T equals to 0 Kelvin, my momentum of each and every particle of that system becomes 0. Yes. The velocity becomes, the speed becomes 0, the momentum becomes 0. Yes. Now understand that if, as for the quantum uncertainty principle, if I know exactly the momentum which is 0, that means my uncertainty in momentum, let's suppose in any direction x, is equal to 0. But I also know that the uncertainty in its position multiplied by the uncertainty in its momentum is equal to, it is greater than or equal to, or if I'll take it as minimum possible uncertainty, h by 4 pi. Yes or no? Okay, let's take greater than or equal to h by 4 pi for the general statement, right? Because we're approaching a limiting case. Now, if the change in uncertainty is 0, this factor is 0, this uncertainty goes up to infinity. The uncertainty of its position becomes infinitely high. That means the system, there is no well-defined system. The system wouldn't even exist. For a definite system, if you talk about a definite system, you know the maximum uncertainty of these particles, right? You will know the maximum. So basically, along the x-axis, let's suppose the uncertainty will you will have one edge at 0, one edge will be at L. So the max change uncertainty, maximum uncertainty in its position could be L. Let's suppose, right? The maximum uncertainty in its position could be x. But then could be L, right? But then what do we get when we cool the system to absolute zero, hypothetically speaking? What happens? All the momentum of each and every particle of the system becomes zero. That means uncertainty reduces to zero in momentum. So the uncertainty in its position becomes what? The uncertainty in its position becomes infinitely high. A system is no more well defined. I hope you've understood this. That is exactly why we cannot achieve absolute zero. Basically, why? As per my understanding, that this is the theoretical limit on this by the rules of quantum mechanics. And since you cannot have absolute zero, the temperature in theoretically also cannot be 0 Kelvin. That means efficiency cannot be equal to 1. Why? Because 1 minus TL by TH, you need this thing to be 0, which is never possible even theoretically. Got it? That will be all. If you have any questions, you can visit thephysicist.in/ask and put your questions there. And see you in the next one. Bye bye.